well, actually not the first. Well, the first thing you need to know at this moment is it's an introduction. If you were expecting difficult, serious, complicated stuff on ROC curves, now is the time to go to another talk. The assumption is you don't even know what a ROC curve is. So that's the kind of baseline. So I just don't want anybody to be disappointed that we didn't go into fifth order ROC curves. These are nice, simple, straightforward ROC curves. So this is me, this is what I do, this is the building I work in. I work at Dundee. I spend about half my time working at the university and about half the time making money. That was an academic joke for those of you who missed it. So I teach a master's in data science, which is a brilliant course. Would you guys agree? So I have 3 of my students sitting here in the front row. And if you want to know about this course, which is done part-time, and is this a plug? Absolutely. Why do you think I'm here? Because we want to attract good students. So if anybody's interested in it, talk to me, talk to these guys afterwards. I'll tell you how brilliant the course is. They will tell you the truth. So this is part of the reason it's good to have them here. Note the word introduction in the title. We are here simply to flatten off the gentle rock climbing curve. There are lots and lots of possible puns about rocks, incidentally, some of which have found their way into this talk. Some of them I really couldn't bear to put in. They were so bad, I put them in and took them out. But there are quite a lot if you think about it. Okay, ROC stands for Receiver Operating Characteristic. Now, this is a highly unintuitive name for what they do. And I did start this, when I first started preparing this talk, I had why are they called ROC curves at the beginning. And I thought, everybody's interested in machine learning. They're not actually here in the history. So we'll do the why are they called that at the end. And it's very easy to do once you understand what they do. So, Ada King Noel, Countess of Lovelace, better known as Ada Lovelace. Why is she important in computing? Yeah, she was essentially the first programmer. She wrote operational instructions for a machine that didn't work very well, didn't really work. She is one of the pivotal people in computing. And Babbage was trying to build this analytical engine, and she said this, and I'll paraphrase it for you. It says they're not going to learn. We call it an analytical engine, but it's not actually ever going to do anything on its own. Machine learning is about them doing things on their own, so that's why we're interested. And you can argue and discuss long and hard about when machine learning started. I think it started with this guy, Arthur Samuel. In 1959, he built a computer program that could play drafts better than he could. I think that's reasonably pivotal. The machine is now doing better at a task that you've programmed it to do. Whether or not we can discuss this, it doesn't matter. But machine learning has been around for a long time. So where do ROC curves fit into machine learning? Because machine learning is a huge, broad field. So the first thing I want to do is sort of show you where it is and where it isn't, where they're important. So we have these 2 classes of learning in machine learning called supervised and unsupervised. I actually really dislike both of these terms because they don't really tell you what it is. I don't think very well anyway. But they are it's a really good divider of the kind of work we do. So the unsupervised learning, we're going to throw all the unsupervised learning away. We are not interested in unsupervised learning. We are interested in the supervised stuff, right? But you still haven't told us what it does, what it is, but at least we're interested in that. Unsupervised learning is where you have data that can be classified, where we're interested in classifying it. So we want to say, okay, we've got all this data about customers. These are good customers and these are bad customers. These customers are male and female, or these customers are female. We are trying to classify things. These insurance claims are fraudulent, these ones are fine. And of course, not all classification is binary. So we are dealing in ROC curves with binary classification. And if you have trinary, quaternary classification, you can sometimes turn it into binary. And if anybody's interested in that, you came to the talk hoping it would be about other forms of classification. We can talk about that afterwards. So this is the kind of data we're talking about. We have some kind of classification that a human being has applied to the data. So we are currently talking about, we are going to build a machine learning algorithm. we have some existing data that has already been classified by a human being. So a human being's gone through and said, this case, when we actually looked at it, it was clearly fraudulent. So this is a human classification, which is often, I think, somewhat ironically called the gold standard of classification. If any of you have ever worked with human beings doing classification, you may spot the irony here. But it's the best thing you're going to get. So this is a human classification of known data. So, okay, with machine learning, we take our training data where we know the answer, and we stuff it through some kind of algorithm, some kind of system that will try and learn what patterns make a fraudulent claim and what patterns make an honest claim. So the system is trying to learn that. This is this is machine learning. It's not even 101, this is about machine learning 1, I think, but just to give you the idea of where we are. We then take the data model that's been produced. This is the output from this algorithm that says these are the rules that make a claim honest or fraudulent. Well, we don't necessarily trust this algorithm. So we say we train it with some data. We typically take all of the data we have that's been classified by a human. We take about 70% of it, and we stuff that through the training algorithm. We use that to train the algorithm to get the data model. Then we take the data model, stuff the test data through where we know what the answer was, and we see how good it is. So we're kind of playing a trick on it. We're saying, oh, no, we don't know what the answers here are. You tell us what the answers are, but we do know the answer, and we check. So it's a very straightforward system. So Roc curves are associated with this testing phase, where we are seeing how good it is. We've got a data model, we've got a set of rules, we've got some data where we know the answer, and we stuff A through B, and we can check it. And just to follow that up, we're not doing all of this for fun. In the end, we want to take some new data where we don't know whether it's fraudulent, stuff it through the data model or apply the data model, and that gives us new information. This is honest, this is dishonest. So we're interested in this testing phase. So, just to use some jargon, you can talk about classifier algorithms, which enables you to say classifiers consistently classify classes into cases. I can't even say it, and I wrote it. So, you can play around with the English language and line up lots and lots of Cs. We're classifying things. Bear in mind that this is binary, so if you say this one is fraudulent, if this one is not fraudulent, that's the only alternative you've got. So we classify things as either this or that. There's no middle ground in here. So you have some data. If you're a genius, you can choose the correct algorithm first time. You can tune the algorithm correctly, you stuff the data through, and you get the perfect data model. If you are capable of doing that, you do not need to listen to the rest of this talk. Mere mortals like me take the test data, we stuff it through a variety of algorithms because we don't know what is the best one for producing the best data model. So we don't end up with one data model, we end up with many data models. So one of the things you have to do then is say, well, okay, which is the best data model? And that's what we're talking about with Roc curves. They are a way of assessing different data models using this testing data that we've still kept back to see how efficient these algorithms, how efficient the models are that we've created. So we're going to be doing binary classification, as discussed. We need generic terms to discuss that. So they can be male, female, good, bad. So the terms that are often used are simply positive and negative. And what you have to do is decide, okay, we're going to decide whether this is fraudulent or non-fraudulent. You have to decide completely arbitrarily which one's going to be positive and which one's going to be negative. If you're going to be doing fraudulent, non-fraudulent, that's easy. If you're going to do male, female, it's a minefield. So are you going to choose female to be positive or male? So I'm making the point this is a completely arbitrary decision you make. It doesn't matter which one you choose, but you've got to choose one, and then the other one is therefore negative. See, I went wild, I did it. I decided to use male, female. I just like living right out there on the edge. I don't care. Naturally, I see the female state as being the positive one. So, each incoming case. So we have a set of data from our website, and we have a known group where we know whether these people are male or female. And what we're trying to do is train it so that it can look at how they use the website and decide if they're male or female. So we have actual females and actual males. And we have the output from the algorithm. The algorithm is going to guess, okay, well, I think this person's female. So you've got to see how this is. These are really females and these are really males. This is what the classification algorithm is guessing. So this is after we've trained it, we're now seeing how good it is at doing this. And clearly there are 4 possible things that can happen. It can be a female and the classification algorithm can say it's a female. That is brilliant. Well done, algorithm. It did a good job. It was brilliant. It can be a female. It can be a male, and the algorithm can say, yep, that's a female. This is wrong. This is a bad algorithm. We need to punish it. It has not behaved well. You do all know you can't punish algorithms, do you? This is just anthropomorphism. So that's a false positive. The system said female, but it was wrong. It can be female, and it can say, no, that's a bloke. Idiot. It's clearly not a bloke. Yeah, it's a bloke. Yeah, it's a bloke. Okay, well, that's a false negative. It's saying not, but it means it is. And clearly, you can have a true negative. This is a male. Yeah, I told you it was a male. We all agree. Incoming data is male, and it really is. Everybody happy with this? You've got 4 possible outcomes. And these 2 are essentially good. I have made them blue to show that they are good. They're getting correct answers. These are incorrect answers. You can also then just label these things TP, FP, TN, FN, and so on. Everybody happy with the story so far? Nice and gentle. So these are very often used. These grids are called confusion matrices. And this is saying these are the actual numbers that we fed in. And bear in mind, it's still test data. We know what the answer is at this stage. We fed in this test data, and this is how it was classified. And you can see it's doing quite well. Mostly, it's got the females correctly, 1,276 of them. Got most of them right. 45 it got wrong. Males, getting most of them right. Some of them are wrong. So it's not doing badly at all. Okay, so we've got a model, and it'll classify into 4 results. How good is it? You're going to have to evaluate it. That's what Roc curves do. We are zeroing in on it. Sometime soon, you're actually going to see a Roc curve. Actually, it's about another 50 slides before we see Roc. Okay, so how are you going to evaluate it? You can say, this one's really good, this one's awful. No, you can't do it like that. We've got to apply science. This is, after all, data science, so we're going to do some science. So this is tempting, but it's not going to work. So the obvious one, I think, is to say, well, how many does it get right? This is tempting, it's misleading. This is going to end up very badly, okay? So I don't want you to think I'm trying to fool you. This looks tempting, but it has a flaw. But one of the things you can do is just take the total number of true positives, the total number of true negatives, these are the right things, divide them by the total and saying it's getting 96% of them right. You see, it's tempting, isn't it? 96% right. I mean, what do you want to get 100% right? It's only a machine. Anybody know what's wrong with that as a measure?
You've got a very, very high proportion that are one answer or the other. Then you could get you even better just by having an algorithm that just says just female.
Absolutely, yeah. So let's suppose I get 99%. Is ACC a good metric? Well, this is the kicker, where you have a very unbalanced input set. So 99 are female, 1 is male. The algorithm has decided, I'm going to call everything female. So here's some data, female. Here's some data, female. Here's some female, female. And he gets 99% of it right. It's a brilliant algorithm and completely useless. Because I can do that. Any of us can do that. So one of the fascinating things about this is this kind of confusion matrix. The input data is quite important to how good it is and how you can measure how good it is. So I'm not saying that this is useless as a metric. Give me an example of where it would be quite useful as a metric. It's the converse of what you said. which is that you said, quite rightly, if they're unbalanced, it's not very useful. If they're fairly balanced, then it's going to be reasonably good. So it's not, none of this is saying this is a bad metric. It's just a metric, and it has good points and bad points. So we need another metric. Grace Hooper. She important in computing at all? Just a little bit? Yeah, she did some really, really groundbreaking work. So it's attributed to her that she said, the wonderful thing about standards is there are so many to choose from. And the wonderful thing about metrics for assessing this kind of analysis, there are lots. How many do you want? I can sell you lots of them. This is just a few. And what I've done is put that up there to remind you where these are coming from. But this list is absolutely not exhaustive. This list is a tiny fraction of all the metrics. And you'll notice that I've got a metric there called, FNR. Well, there's a whole list of metrics that build up on these primary metrics and then build them into more complex metrics. You can have as many metrics as you want. So, we're not short of metrics. The trick here is to know the strengths and the weaknesses of each one and apply them intelligently. And that, if you take a take-home message from this talk at all, that's the one to take home. None of these metrics are bad. They just have characteristics, good and bad. They have good points and bad points. So this is just to show you that they build up into more and more complex metrics. The good news everybody, ROC curves only use two of them, and they use two quite simple ones. They're so simple you can actually understand them. Some of the metrics are pretty abstract. So the two we're interested in are the true positive rate, also called the sensitivity or the recall, the false positive rate, also called the fallout. And what I've tried to do is explain to you in words of English what that means. Because we're going to be plotting one of these against the other, we're going to get patterns, and you guys have to be actually able to actually understand what that pattern is. That's the point of this talk. So this one is simply saying, take the true positives, these are these, which it gets right, and divide that by the true positives plus the false negatives. Now that is, of course, equal to that value. So it's saying, essentially, okay, we input 1,000 females. It got 900 of them right. So that metric will come out to be 90%. It's just simply telling you how many of the positives it got right. And you subtract from 100 and you've got how many it got wrong. It's very straightforward. The second one is slightly, slightly less intuitive. It's same calculation, but it's taking the false positives and dividing those by the false positives and the true negatives. So it's calculating the number of negative examples that are incorrectly classified. So the first one is saying, how many did we get right? And this one is saying, how many did we get wrong? Or how many of that class did we get wrong? I'm pausing so you can work that through your brain. So this one is saying it's the fraction of the negative examples that are incorrectly classified. How many of the males, in our case, females were positive, males were negative. How many of the negative ones are incorrectly classified? Everybody happy with that? This one is, how many of the positives did we get right? How many of the negatives do we get wrong? Okay, this is not a ROC curve. You're not yet. You're not getting away that easily. You're going to have to work for this. But this is gloriously called Roc Space, in which we can plot ROC curves. So this is Roc Space, and it's plotting FPR, which stands for, I can't remember. Thank you very much. Louder.
False positive rate.
See, brilliant. And this one, therefore, must be the... Guys, I'm working hard here. You're not with me. This one is the true positive rate. Okay, so this is how many of the good guys you get right. This is how many of the bad ones you get wrong. They're not really bad ones. They're just true and false. Okay. We have a baseline here, and we can say that all classifications should be above this line. And I say should be. They will be by the time we've finished with them. You can't get an answer down here. Now, I realize you're all regarding that as a challenge, and you're all thinking, no, no, I bet I can get one down there. Okay, I'll show you why you can't get one down there. Here is some data. This is a confusion matrix. We have 25 positives and 75 negatives. These can be females and males. These can be people defrauding or not defrauding our company. It doesn't matter. They're now these abstract positive and negatives. And what I'm going to do with my algorithm is going to be really simple. In fact, I have the algorithm in my pocket, but I can't get to it from the microphone. Okay, my algorithm is this. The first one comes in, and I get the data. I don't even look at the data. I go female, or I go negative. Next one, positive. I'm guessing entirely at random. My algorithm is just doing random stuff. It's just generating random decisions. And if you do that, then these are positive, and it's going to get half of them right and half of them wrong. Because, sorry?
Just wondering how you get 12.5 people right.
Yeah, you have to use a saw, and it's messy, and so we're chopping up these people. These guys, you're going to get the same thing. And of course, these two values are calculated. If you take that one, divide it by that one, you get that one. And it's true that'll give you 0.5. I've just turned it into 50%. I'm just multiplying by 100. To get the other one, you divide that one by that one. And all of a sudden, you can see that no matter what you do, you're going to get a point that is there. It's 50-50. And there's nothing you can do about that. And if you look at these figures, what I'm doing here is changing the input values, because that would I chose rather arbitrarily 25, 75. You can swap those around as much as you like. It doesn't make any difference. You still end up with 50-50. What's the other set of numbers I could change on this confusion matrix? Well, I could change the bias of the coin I'm flipping. I could 80% of the time say female and 20% of the time say male, or 99-1. I can change these numbers. And the interesting thing about that is if you change those numbers, which is what I'm doing there, it just shifts this up to there. So it doesn't matter what you do, if your algorithm is choosing numbers at random, you will get a point on that line. Clearly there'll be variation because there'll be noise in the signal. But basically you're going to get something on that line. And you think, but a machine learning algorithm is not going to sit there and flip a coin. You're being unrealistic. Okay, but what I'm saying is if the machine learning algorithm has been completely inefficient and it's generated a completely silly set of rules, you're going to get essentially random behavior. So it's not that we expect it to be a random number generator, but if it is woefully inefficient, it's going to behave like it's making random decisions. And you're going to get on the line. So one of the nice things about ROC curves is anything that isn't on that line, anything that deviates from that line is interesting. Anything that's on that line is behaving so badly we are completely not interested in it. We have no interest in it whatsoever. So anything above the line is doing better than average. What happens if you do get something below the line? What does that mean?
Negative correlation.
It's negative. So what it means is when a male is coming in, it's far more likely to say female. And when a female comes in, it's far more likely to say male. Okay, so that's completely useless, isn't it? Work with me here, guys. If you have an algorithm that's doing that, what do you do? You should invert it. You say, okay, it's got the data in and it's saying female. We know that it's not very bright. So we're going to reverse that and say, well, actually, it thinks it's male. And if you do that, lo and behold, it jumps to there. So when I say you can't produce an algorithm that produces down here, well, you can. But if you get one that's producing down here, it's really good. You've just got to invert it. So everybody happy with this? This baseline is very important in ROC curves because that is your baseline. That's it. You're going to work up from that, not down. Okay. Do you remember earlier I said what happens if you're using ACC and reality is 99% positive and 1% negative? And I said that ACC dealt with that very badly. Well, clearly we're interested in popping that into Roc Space and seeing where it turns up. And the answer is that it is saying always positive. So we're feeding in 99% female, 1% male. It's saying female, female, female all the time. It's 100% saying female. That ends up there right on the line. Because it's not doing any good. It's not actually productive at all. And ROC curves are sensitive to that level of inefficiency. What would make this really amazingly accurate? What do you have to change? So this is the incoming data, 99% of the female. It should say 99 female. What should it do with this one lone male? How should it classify him? Male. Hey! Good or what? It flips it completely. This is the best position on a Roc Space. Top left-hand corner, brilliant. You are as far away from this line as you can get. Look at that, isn't it amazing? Nobody, incidentally, would do this on these kind of numbers with 100. Do not think I run on sample sizes of that size. These are just illustrative. But it's fascinating. It's really sensitive to this kind of accuracy. It's one of the reasons we love ROC curves. So you got some data. You build a model, you try it. You build another model, you build a third, you build a fourth, you build a fifth. Each one of them is going to produce a point up here. This is actually the data I showed you earlier, which was data I was showing you about females and males. And I said it's getting quite a lot of these right and quite a lot of those right. That ends up there, which is really good. So that intuitively looks good and it gets a good score. You'll notice that these are still not curves. These are just splats on a graph. So you are beginning to feel significantly misled at this point, because there's no curve. Where's the curve? Okay, this is not yet a classic ROC curve, but it is finally about to appear, because there is a zombie apocalypse. So you may or not have noticed, you're locked up in this hotel room, there are zombies out there, as of this morning. You haven't been checking the news feeds. And it's a bit of a problem because, well, who wants to be a zombie, eh? So zombies are infected typically by being bitten, but they don't necessarily show the bite marks. So we've got some people. We're all fine, incidentally. We're all okay. Because we've been here for, let's imagine we've been here more than 48 hours. So we got people, and we think they're infected. We're not sure. So we got them in a cage, which is nice. And we've done some research work on this, and zombies have a higher antibody level for a particular antibody than normal people. So we're going to try and work out who's infected. The good news is we have a lot of background data. We have 2,000 individuals who are healthy, and for this particular antibody, they have a mean antibody level of 100. The infected people who are going to turn into the living dead have an antibody level of 110. And the standard deviation is exactly 10 in each case. Anybody think these figures are just a little bit convenient? Does real life give you these numbers? Of course it doesn't. But I want to show you, I want you to be able to actually understand the figures I'm showing you rather than me saying, and you'll have to take my word for it that they're like this. So the reason for convenient numbers is to make it easy to, actually make it easy for me to describe. Just to refresh, those of you who are, depends whether you use stats a lot. There is a nice thing about normal distributions. If you have a mean of 100, then 35% of all the values will be between 100 and 90, and that's one standard deviation away. And if you're a statistician, you are falling asleep at this stage. You learnt this when you were 3. If you're not a statistician, then just take our words for it, that if you have a normal distribution, you can make very precise predictions about how many people will fall into each class. So what this is saying is, if you're a healthy person, a group of healthy people have an average antibody level of 100, but any one healthy person has a 35% chance of being between 90 and 100. They've got a 0.5% chance of being underneath 70. So we can make nice predictions from these. Well, okay, so we know then quite a lot about this. This is the antibody level. Here are the healthy guys, and here are the infected guys. Okay. Just as a side issue, I know this occasionally causes people confusion. If you go and sample those people in the cage, they're probably a bit cross with you because you put them in a cage with other infected people, but assuming we can take blood samples, you're not going to see two curves, of course, because they're a mixed population. You don't know who's infected or not. So you've got to put the two together, and what you'll see is a distribution like that. The guys down here are almost certainly healthy. The guys up here are almost certainly infected. It's the guys in the middle we're not sure about. And we need some test where we can put a stake in the ground. Sorry, it's more vampire-ish, isn't it? But you can put a stake in the heart, and you can say, above this level, they're probably vampires. Sorry, zombies. And below this level, they're probably healthy. So if we know who's healthy and who's infected, then we're going to see two overlapping curves. So, okay, I'm going to put a stake in the ground. I'm going to say everybody above that antibody level is about to join the living dead, and these guys are going to be healthy. They are healthy now, and they're going to be fine. And you think, well, I wouldn't put the stake in the ground there. True, okay, where are you going to put it? Because wherever you put it, what you're going to be doing is changing the balance of true positives, true negatives, false positives, and false negatives, because that's what's going to happen. This is a brutal classification system. It says you're on one side or you're the other. And if we look at just the healthy guys for the minute, just these guys, if we put the stake in there and say here be the living and here be the infected, these guys are all healthy. So these are all true positives. These are all going to be correctly identified. These guys are all condemned to, well, sorry, no, not condemned to. We have classified them as zombies, and they're not actually going to be. So these are false negatives. We've said these are healthy, we're right. We're saying these are unhealthy, and we're wrong. And you think, well, you need to shift this way over here, man. And why have you put it in the ground here? Well, there's the other guys. Because if you look at these guys, it's the other way around. These are all true negatives. These are all correctly classified. These are the incorrectly classified ones. So this is one reason why this simple splitting into these four categories is so useful for us. So what we can do is slide this threshold up and down and see what numbers we get from it. Now, if I put a stake in the ground there and say, well, everybody on this side is a zombie. Now, if your mother was in that cage, would you be happy with me doing that? No, you wouldn't. It's a stupid thing to do. We're not really suggesting you do this. Well, it depends how well you get on with your mother, actually, now I think about it. But we're just going to see what happens. Well, what's going to happen? We're going to say everybody on this side is healthy, everybody on this side is zombie. Who is correctly classified? Well, I don't expect you to be able to point from there. These guys are correctly classified. Everybody else is incorrectly classified. Sorry, all of these guys, I beg your pardon, are incorrectly classified. These guys are all correctly classified. So, TPR is the fraction of positive examples that are correctly classified. These guys. The FTR is the fraction of the negative examples that are incorrectly classified. These are all negative, because we decided healthy is positive. These guys are all negative, and they're all correctly classified. Sorry, yes, they're all correctly classified. None of them are incorrectly classified. So it's working very badly for these guys and very well for these guys, except they're zombies. That's a bad thing for them, personally. So we've got 0.05 and we've got 0. Move along. These guys are correctly classified. These guys are all incorrectly classified, and we're just beginning to get a tiny number of these guys incorrectly. So this has gone up to 2.5%, and this has gone up to 0.05. Now you can tell what I'm going to do. I'm just going to march across the graph, obviously. So we can go through these next slides pretty quickly, and in fact, if you're really lucky, I'll go backwards, and you can see it almost like an animation. So as we go through, we're getting more of these guys. So the FPR is going up, so we're going up there, and we're not going very far along there, because it's only these guys who are moving us along that line. So one way to think about it is these guys are moving us up, and these guys are moving us that way. And remember, we want to be above the line. So as we march our way through this, it does that. Let's go backwards. Let's go forwards. And what shape is that making? It's a curve. It's right, fine. With 5 minutes to go, we've actually got a rock curve. It's brilliant. So they are very, very important estimators of algorithm efficiency. And you notice that there's a lot that's not on there. What we're not showing is what threshold we used. This diagram is not concerned with the threshold we used. It's concerned with the value of one against the other, and that's all it's doing. So if the curves are further apart, what's going to happen to that rock curve? You can now answer, I was going to say you can answer by drawing in the air, and you did it. And it does that. It gets further across. So that's the one we started with. It's pushing it in that direction, which is exactly what you'd expect it to do. And you can take this further. If those two are almost completely separated, it's basically that shape. If they overlap completely, it just goes straight up the baseline. So these rock curves are really good for distinguishing them. Clearly, then you can start looking at metrics like the area under the curve, which is of interest to us. How much area do you have under this curve? So, does the rock curve tell us where to put the classification? No, it doesn't. It's a help, and it gives you more information. But what it doesn't bear any thought about is what's the cost of a false positive and what's the cost of a true negative. What do these things actually cost you? And, of course, if you're zombies, well, where are we? So people judged negative are caged together. Suppose we did that. We say, okay, anybody who's negative, who we think is a zombie, we're going to leave them in the cage. Everybody else we're going to let free. Well, the problem for that is the people who are healthy in the cage die. And the worst news is, I mean, that's bad. But it gets worse, because everybody we release is infected. Everybody we release who is infected, they go out and they bite people. And it's the end of society as we know it. What I'm getting at here is the consequences of these things are very different. And, okay, let's pull back from the zombie apocalypse. If you have fraudulent transactions, a false negative may cost us the value of the transaction. A false positive may really annoy the customer. So you can't just use a rock curve to say where you're going to put the flag in the ground. You can't do it. But they are still really useful. So where do you set the threshold? I don't actually have an answer for that. Bear in mind, there are lots of these other metrics you should be looking at. They all have strengths and weaknesses, just like rock curves. And it is a really good idea to get to know these metrics well. What are they good at? What are they bad at? Under certain circumstances, you would never use particular ones. But I see them being used incorrectly by people who don't understand them. By a bizarre twist of fate, there's an article on the BBC website about the origins of radar. And that's appeared today. And it's germane because rock curves have their origins in signal detection theory. Now, to add another definition, the rock is a mythical bird. Have you heard about this? Yeah, big rocks, right. These are not real. You do not have to worry about rocks. But they're mythical. This illustration, which I found, it doesn't really give you an idea of the scale. The rock was an extremely large bird, as you can tell by this illustration, which I think gives an idea. Now, suppose you wanted to find rocks. If they did exist, we would want to know if they were approaching London. I think you'd all agree. So we'd invent radar. And when radar was being invented, people were very interested in interpreting it. Now, this is a diagrammatic representation of radar. There is no rock here. Here be rocks. Okay, it's very straightforward. And if the screen is dark, there aren't any rocks. And if the screen is light, there are. And if you look at the intensity, where would you put your threshold to decide if there's a rock? Well, it doesn't matter. You can put it anywhere there, because anywhere in there will distinguish rocks on this side, not rock on this side. Unfortunately, it wasn't quite like that in the early days. It was fuzzy and blurry. And is that a rock or not? Is that a rock? Maybe you improve the set a bit. Is that a rock or not? And actually, if you start looking at the signal to the not signal, guess what? You get a pair of curves. And guess what? These guys were very interested in deciding what was a signal or not. Does that look at all familiar? Right, that's the origin of rock curves. You can apply rock curve technology to this, which is what they did. And that's where it comes from. It has nothing to do with machine learning. What we've done is stolen this technology from people who designed it.